So, good evening. I think because of this short notice, uh, there are no people who have joined. So, but I told you this. What happened to this screen? Just wait. Mm, okay, let me disconnect and then I will come back. Just wait. Yeah, I think it is now. Yeah. So maybe because of this short notice, I think most of you are not able to get that mail, but it has been sent. And I also told you in that this Tuesday session that we will be having a session on this Friday because we are approaching in the almost at the end of this live session series and also the end of this course. So that's why it was good to have this Friday session. And after this, we will be having one last session on Tuesday. So yeah, next week Tuesday we'll be having one last session. That will be I think I will be discussing about like all the assignment questions in that till now from week 1 to week 12, which the questions which were good, like which need to be look upon again. And um, and yes, so I think your exams are probably next to next week. I don't know the exact date, but I hope you are preparing well for that. And anyway, like even after the last live session, that is on next week Tuesday, we will be having we so you can like text us or like on that discussion forum, and if you have some requests or something, then yeah, we will be love to like share or like clarify your doubts in that discussion forum. So yeah, so today in Friday, this today like in this session we will be talking about this week 12's assignment questions which were from previous year. And first of all, welcome again to this electrical measurement and electronic instruments course. And yeah, so we'll be going through some of the assignment questions and then we'll see some of the extra questions too, which are related to this op-amps and all. So like last week, not last week, this Tuesday I told you about this Lesage's patterns. So where like I committed one mistake in that, so sorry for that. I will be clarifying that here. So if you can write somewhere, I will write it here by adding a page. Just wait. So I was talking about this Lesage's patterns, and I drawn like based on the phase difference. I draw different types of these patterns. So I want to draw them again, so that equals to zero. Anyway, this is a recorded session, so whenever you get time, just look into the session. So we had this 0 to 90, then 590, then we had 5 from 90 to 180, then 5 equals to 180, then 5 from 180 to 270, 5 then equals to 270, then 5 from between 270 to 360, and finally 5 equals to 360. So whenever there is this phase difference 0, then we have the straight line. Between 0 to 90 we have an ellipse like this, and then for 5 equals to 90 we have a circle. then this cubes in another way from 90 to 180, then phi equals to 180, it is this, like so you can see the difference between these two. So it is like skewed in the like in mirror position, in mirror reflection to the phi equals to 0 with respect to the phi equals to 0 angle in phi equals to 180 case. Then we have 180 to 270, that is this ellipse. Then we have again this circle. Now we have ellipse in this direction, and then for 360 we come back to phi equals to 0. So this is the pattern which you can remember. So if you know this, then you can. It's also earlier, like I missed this one. So now I am like, because of that, like the patterns which I drawn earlier, so they were wrong. So but yeah, so these are the right patterns now. So moving ahead, so in this practicing these assignment questions. So the first question which we see here, it's like in the above, so it is saying that in the above Lissajous figure, obtained using two sinusoidal signals in the XY mode of an oscilloscope, if the frequency of Vy is 350 Hz, then estimate the frequency of Vx. So I have told you the formula, like the formula for frequencies of two signals, basically the ratio of the signal at Y input and the ratio at X channel equals to the horizontal tangent cutting points, I will say tangent cutting points, and then we have vertical tangent cutting points. So so this will be maximum, so maximum number of times it is cutting, these tangents are cutting through that through that diagram, through that pattern. So similarly, maximum number of times cutting vertically. So if we see this figure, then if we draw a pattern, I will draw from another line. So if we draw a horizontal tangent, then so maximum number of times it can cut this figure is like 1, 2, 3, 4. So 4 times. So we will have 4 here. Then if we go for vertical, then we can cut that like this, 1, 2, 3. So it is 3. Now Fy we know, that is 350. Fx we don't know. So Fx will be 350 into 3 by 4, and this will be 15, 16, 14, 10, 5, 5, 5 3 are 2, 3, 525. I'll just check. This is 525. Yeah, divide by 2, which is equals to 262.5. Okay, so so these kind of, I think just you have to keep in mind, like you have to cut these patterns maximum number of times horizontally as well as vertically. Then I think this, if you remember this formula, just keep in mind, if you are going for y-axis, then we talk about the horizontal line, horizontal cutting points. But if it is x-axis, then it is vertical tangent, so it is reciprocal. Okay, so this is fine, I think. Then the next question. So this question is like this says that there is an emitter follower. So we have emitter follower voltmeter circuit. VCC equals to 15 volts. So this VCC is 15 volts. The full scale deflection current of the PMC meter is 2 milliampere. So we have VCC equals to 15 volts. Okay, full scale deflection 2 milliampere. Okay, and it has an internal resistance of 350 ohms. So let's say this internal resistance is Rm. So this Rm equals to 350 ohms. So this is the internal resistance of PMMC meter that we have seen in the initial lectures of this week 1, week 2. The PMC also have their own internal resistances. So the BJT has VB equals to 0.7 volts. Okay, VB is given 0.7 volts, and beta factor is 249. Now they are asking estimate the required value of resistance RS. Okay, RS, this one, to obtain full scale deflection for V in equals to 4 volts. So they are saying they need this full scale deflection, and when it will be full scale deflection, when V input, that is this voltage, that will be a 4 volts voltage. Then they need this full scale deflection. For this to happen, what will be the RS value? So if we see this diagram, let's say if we go like this, okay, so this is IE, that is fine. So we will use KVL in this loop which I have drawn. So we start from V, if we start from V in, so V in minus, so there is a drop across this base emitter. So this is the base of this BJT, this is the collector junction, this is the emitter junction. So the drop across VBE is given by, it's already been given, that is 0.7 volts. So this V in, then there is a drop of minus VBE, then we move towards RS, and then there is again a drop of IE into RS, because emitter current is flowing through RS and as well as PMMC meter, minus PMMC meter is having a resistance of RM, IE, and that is all equals to 0. So we created a loop and use KVL in this loop, okay, in this loop. So then if we solve this, so we have V in, we have to maintain V in as as 4 volts, then VB is given 0.7, then IE we okay, so they are saying this is for full scale deflection. So when that there is full scale deflection, so we know what is the full scale deflection readings, that is 2 milliamperes. So IE is 2 milli. Then we don't know RS, because now the main question is to calculate this RS. So RM will be, and now RM we know, that is 350 into IE is 2 milli equals to 0. So this will be 3.3, then 2 milli equals to RS plus 350. I'm just rearranging the terms here and there. Then by 2 milli minus 350 equals to RS. Okay. Now if we solve this, so this will be 3300 by 2 minus 350 equals to RS 650. So this will be 003 1300 ohms is our RS value. Okay. So I think so if you know about this B base emitter junction, so then you can you can solve this. So this is just KVL you had to apply, and you wanted to, you should know about this base emitter, how it behaves uh, in forward bias, and then you can solve this. Now based on this only, the next question is for the above value of RS. So for the above value of RS, that which we have calculated here, estimate the meter deflection for V in equals to 2 volts. So what happened earlier, this V in, so this V in was 4 volts, and for 4 volts it was giving full scale deflection when RS we calculated was 1300 ohms. Now they are saying RS remains same, okay, RS equals to 1300 ohms. Now they are saying estimate the deflection, that means estimate the emitter current, because it is the emitter current only which is passing through this PMMC meter. Hmm? So this is the emitter current IE, we don't know now, that we have to calculate. But we know that V in is now 2 volts. So again, using the KVL, mm, that is V in minus VBE, the base emitter junction, minus IE into RS plus RM will be 0. Now we know V in is 2, we know VBE, that is zero point 0.7, we know RS, that is 1300, and RM is 350. So in total it becomes IE is equals to 1.3 divided by 0.51650. So if you calculate this, then you get 0.787 milliamps. So now you need percentage deflection. So just keep in mind what the question is asking. So like if you will be in a hurry, then you can directly go and fill this value in that numerical based question. But here they are asking for percentage deflection, so it will be given based on the full scale deflection. So we have 0.787 divided by full scale deflection current is 2 amperes, 2 milli. So this was 0.787 milli. So we will get approx 39 percentage of deflection, of full scale deflection. So basically it will deflect only till 39% of the full scale value. That is this question. Okay. Now the fourth question. Determine the input resistance of this emitter follower voltmeter for V in equals to 4 volts. So they are asking now the input resistance for this emitter follower voltmeter V in equals to 4 volts. So I will tell you, like so whenever you need to calculate this input resistance or impedance, the basic funda is that you should know the input voltage to that. So let's say there was one black box, you don't know what is there inside that, and then you need to calculate the input impedance or resistance of this black box. So simply you have to keep in mind the voltage drop across the input side and the current being given from the input side into the black box. So if you know these two things, then you can easily get Z in. If it is only resistance, then R in. Okay, so this is the basic funda. So now we know V in, we know. Now what is I in? So we know that when V in was there, I in was how much? I in was full scale deflection. So we can say V in equals to 4. That implies I in is is equivalent to full scale deflection, but base current. So now the trick here is that now we are talking about the base current. Why we are talking about the base current? Because this is the base current which is flowing inside this system or this emitter follower. So it's not the emitter current, it's the base current. So now if we know this beta value, then we can calculate this IB also. So I will say just IB in this case. So IB, you know this famous relation, that is IB plus IC equals to IE. That implies IC, we can write beta IB. So IB we can take common, it will be 1 plus beta equals to IE. Now if we know IE, that we know that is 2 milliamperes. So IB will be 2 milli divided by beta plus 1. So beta was 249. So it will be 250. Okay. So it will be 250. So we will get this 2 milli by 250. How much it will be? 0.008 milliamperes. So we know this is the input current, that is IB. So R in will be V in by I in equals to 4 by IB equals to 4 by 0.008 milli. So this will come out to be 500 kilo ohms, that is R in. Okay. uh yeah, so what we did, so we had this base emitter follower, and we knew about VCC, we knew about full scale deflection value of this PMMC meter, we knew about RM, that PMMC meter internal resistance, we knew about this base emitter junction diode voltage, forward bias voltage 0.7 volts. Then we knew this beta. So based on that we simply used KVL, and we came up to the conclusion that the RS for maintaining V in at 4 volt and at the same time maintaining the full scale deflection current, the RS will be 1300 ohms. So after that, keeping that RS same, we decrease the input voltage, and then we come to know that for if we decrease the input voltage, then we change our emitter current, and that emitter current is basically the current through the PMMC meter, and it changes the deflection. So how much percentage deflection we changed through that? We came up to 39% of that full scale deflection. Okay, so we actually reduce the deflection of that PMC meter by reducing the input voltage. Then in this series of three questions, then in the last there we had this V in 4 volts. We needed to calculate this input. We needed to calculate this input resistance. Then for that, what we did, we knew V in, that is input voltage, but the input current was the base current. For base current, we used the relation of the base, collector and emitter currents, that is IB plus IC equals to IE. Then we knew IC is equals to what? Beta IB. We used that relation again, and we came up to the conclusion that IB is that it is equals to IE, the emitter current, divided by beta plus 1 factor. So then we got IB, and then we finally got RN. So this was about this base emitter follower question. Now the next question. So the next question says that if two sinusoidal signals with the same frequency and the same frequency and same phase angle are applied to the X and Y channels of an oscilloscope, then the curve seen on the screen will be. Yeah, by the way, one more thing I want to clear, that I think this is only for the signals which are having same frequency signals. If their frequency is different, then I think this will not. Same frequency signals. Okay. So curve seen on the screen will be, so they are asking for a curve. So the phase angle is 0, that is saying the same phase angle, frequency is same. So what we'll get a straight line. Okay, I think this is straightforward. And we can see here also, since when it is 0, so it is a straight line. Okay, the next question: how much is the minimum required sampling rate for a digital oscilloscope to capture a 12 megahertz sinusoidal signal? So based on Nike's criteria, it is always 2 into 12 times of the input signal. The sampling frequency is always, it should be greater than fs, should be greater than 2 times of the signal frequency. So this is sampling frequency. So it will be greater than 24 megahertz. But like empirically or like in practical cases, we normally take 10 times of 2f signal. So this is just for your knowledge. This 10 times of basically frequency of the signal. So this just for the knowledge, as like whenever you will be like acquiring some signal. So if you set just 2 times of the input signal frequency, that the frequency of the sampling rate, then you will not get that good representation of your input signals in oscilloscope, or either in this analog to digital converters and all those things. So at least you need 10 times, but for the sake of the question, it is 2 times minimum. So minimum is 2 times you will get the signal. But if it is less than 2 times of your input signal frequency, then you will not get that at all. But in order to increase the resolution of that, then you need 10 times of the input signal frequency. So yeah, moving forward. So again, the decisive figure we have, and we have this in the above decisive figure. obtained using two signals in the XY mode of an oscilloscope. Okay, with the frequency of Vx, so they have given the Vx frequency, that is the X channel frequency. So we have Fy by Fx equals to that horizontal tangent number of times the horizontal tangent is cutting that figure, maximum number of times, and divided by the maximum number of times vertical tangent cutting that figure. So if we say horizontal, just keep in mind it should be maximum number of times it should be cutting this. So it is like this, I think. So 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. Now if we go like this, 1, 2, 3, 4, 5, 6. So this is 6. So using this, Fy will be 8 by 6 into 450, and the final results for this will be 600. So this will come out to be 600 hertz. Okay, so this is the frequency of the Y signal. So this is easy now. So this kind of questions are easy for you to calculate, to solve. So just remember the formula, just remember the relation, that is kind of reciprocal to that what you have on this LHS. Like you should not accept that it is the Y number of, it is in the, it is this vertical line, but it is the horizontal in the numerator. But anyway, the next question. So next question again we have one this BJT, and so if you read the question, then it is it is being written that the above linear ohm meter circuit assumes the beta value of the BJT to be very high. So when you assume this, what does that mean? Beta is very high. I'll say just high, very high. So that means, so we had this we have this relation that uh, I beta IB. So IB is basically the base current. Beta IB equals to the collector current. Okay. So what will be IB? IB will be IC by beta. Since this is very high, that means IB we can assume to be almost zero. So if the base current is zero, then there is no current flowing through this branch. So if no current is flowing through this branch, then we can say what is the voltage drop at this point, that is VB. So VB will be equal to 15, simple voltage divider concept using this and these two resistors. Okay, 15 divided by 15 into 930. So we are talking about the voltage across 930 ohms, that is VB. It will be 930 divided by 930 plus 570. It will be 15 into 930 divided by 0 and 10, 10, 15. 1500 I think. Yeah. So yes, it's 1500. Just calculating this. 9.3 volts. So we get VB equals to 9.3 volts when this IB we are assuming to be 0. Then if IB is 0, again we can deduce another relation, that is between collector current and the emitter current of the BJT. So we know this is an NPN. Yes, I think this is an NPN BJT. So we have this emitter here. So IB is not there, so IC is there. So IE is approximately equals to IC. Okay. So when IE is approximately equals to IC, so we have this one more relation now. So what they're asking what is RX. So if we somehow know IC, then we can go get to know what is this V voltage. Now what is RX, because yeah. So what we can do? So can we use KVL starting from here, going from this branch then going from this base emitter junction, and then going through VB and then ending at this ground. Let's see if we can do that. So the first voltage is what? It is 15, starting from 15. Then there is a drop across this 10,000 ohm resistor, and that is having drop of IE into 10,000 because IE current is going. Then we have this VBE drop. Then we have VB, the drop of this across 930 ohms. And VB we calculated, I think that is 9.3 volts. So if we just use that in this equation, 14.3 minus 9.3 divided by 10,000 equals to IE. Okay. Yes. So then we have IE equals to zero point 0.5 milliamperes. So if we have IE equals to zero point 0.5 milliamperes, then so we needed this RX. So we know IC will be going through this because they have mentioned that voltmeter resistance is very high. So there will be no current through voltmeter. So all the current will be passing through RX, and then we have the voltage drop across V is, or RX is, V equals to RX IC. RX we don't know, that what we have to calculate, zero point 0.5 milli equals to emitter current, and V is what? V is 2.7 volts, it is being given there. So 2.7 divided by zero point 0.5 milli, we get Rx, and this will come out to be 5 for 5400 ohms equals to Rx. Okay, for 5400 ohms Rx. So this is the thing. Yes, so yeah, they ask for ohms, so it will be 5400. Okay. Now moving to the next question. Again, it's simple. Like we need to calculate Vy we know, and we need to estimate Vx. So again, that Fy by Fx equals to, we cut through this vertical and horizontal tangent. So horizontal will be 2, maximum points 2, and vertical 1, 2, 3, 4, 5, 6. So this is 6. We have 1 by 3, and Fy is 100 into 3 Fx. So Fx will be 300 hertz. Okay, so this is, I think, now you have a grasp on this kind of questions, this pattern based questions. So if you want to, so next question is, if you want to see 4 complete cycles of 60 hertz power line signal in an oscilloscope, then how much should be the frequency of the time based signal of the oscilloscope? So if you want to see, so they are asking like if 4 complete cycles they have to see for 60 hertz power line signals to oscilloscope, then how much should be the frequency of the time based signal? So it will be simple. I think you have seen this in lecture. 60 by 4, which will be 15 hertz. Okay, so this is 15 hertz. So this was all about this week 12's assignment question. So I think this is some lag in what is being shown there and what I am seeing here. But anyway, so yeah, so this is about the assignment questions. I think we have done all the assignments from week 1 to week 12, and there were a lot of questions. There were a lot of questions to practice uh, based on these assignments. And so if you get any doubts while solving, I think you still have a lot of time to submit week 12's assignment, and I hope you will go through this and you will be able to solve those questions. Then yeah, so yeah, okay. So now, So since this is done, so I had some extra questions. Since so we will be, I will be solving that, and we will be looking into these extra questions. So yeah. So, so if you are like, if you will be seeing this as a recorded session, so just read the questions. So read this question. So yeah, I'll just take a pause so that you can read the question, and then you can think, and then I will start. So I hope you have read the question, and so let's see. So what's the question is saying? So in the diagram given below, determine the deflection of the ammeter with a full scale deflection of 1 milliampere when the switch is at 2 kilo ohms. So the switch was at 2 kilo ohms, and determine the deflection of the ammeter. So they are saying basically for the full scale deflection, that is 1 milliampere of this PMMC meter which is here, the switch was connected at, oh okay, okay. So they are saying that there is a full scale deflection of 1 milliampere, that is fine. Determine the deflection of the emitter with a full scale deflection of 1 milliampere with the switch. So they are asking like what will be the deflection, what will be the deflection of this PMMC meter when the switch is connected to the 2 kilo ohm 2 kilo ohm resistor. Okay, so this they are asking. Now you should think like this, like when this full scale deflection will be happening. So will it be at 13 kilo ohms or 10 or 1? So if you see, let's say we have some voltage that is V in here. So if V in divided by some resistor, we'll get the current here. So at a time with this switch only one branch is connected, so that current will, let's say if it is flowing from any of the branches, it will be the same current which we are seeing here. It will be same here, and it will be going ultimately to the PMC meter. So the the observation here is that the current which is being flown into these branches, one of the branches, is being fed directly into the PMMC meter, because we know the no current will be flowing inside the operational amplifier. In that case, so this V in by R, so this will be zero, okay, because of this virtual short. Oh, I think there's some mistake. So this is negative. This will be positive. Let's change that. Yeah, that is important actually, feedback. So based on virtual short, this is zero. This is V in. So V in by R is I. So if R, so if you observe this, so when I will be full scale, that is when I will be max. I will be max when R will be minimum. Okay. So if R is minimum, then only I will be max. So when they say that there is a full scale deflection of 1 milliampere, so what is the only possibility when this will be 1 milliampere? The only possibility is that when we only have this 1 kilo ohm of that branch resistor connected to the switch. So that means R we have is 1 kilo ohm. So V in divided by 1 kilo ohm equals to 1 milliampere. We'll get to know what is V in. That is 1 volt. Okay. Now, if you know V in, so what will be the current when 2 kilo ohm is 2 kilo ohm resistor is there? So it will be V in by 2 kilo, that is 1 divided by 2 kilo, that is 0.5 milli. So we get zero point 0.5 milli in this case, and this zero point 0.5 milli is what? Is half of the full scale deflection. It is half of 50% of full scale deflection. Okay, so we will have this half scale deflection in the emitter. Again, I will let you. I'll, I'll give some time to think. So just think this, go through this, read this, and try to answer. So the question is saying like calculate the change in the output voltage if the photocell is exposed to light of 0.61 lux. Lux is the unit of light, intensity of light from a dark condition. Specification: assume that the op amp is initially nulled. That means it is being there's no offset there. That is so there are so many techniques to null the offset or the bias current of that offset. So somehow they have nulled this op amp. Okay. Now they are saying that minimum dark resistance of this op amp is 100 kilo ohms, and resistance when illuminated at 0.61 lux is 1.5 kilo ohms. So they are saying like how much change in the output voltage will be. So the for this percentage for 0.61 lux, yeah. So this you have to calculate. So in the options also you can see that. So you have some ranges from 23 to 50, 0 to 33.11, then 1 point, then minus 11653 to 8.98, and minus 0.17 to minus 11.73. So this is the photodiode we have. Its resistance will be changing based on the intensity. So I think you might have heard about this LDRs. LDRs, these are kind of sensors which acts like this only. So when if you like if the light intensity changes in that LDR, and then their resistance changes. So I think these are being used in lots of, I think you have used in your BTech projects, first year, second year, whichever projects, but these are there. So yeah, you just think. So the first thing, like which we'll have to see, is that, see, we have this two resistances. One is this minimum dark resistance, that is like this is maximum resistance. Minimum dark, okay, when dark is minimum, so this resistance is maximum. So max resistance of, I'll say this, photocell equals to 100k, and the resistance at which it is exposed to light, which is given in the question, that is 0.61 lux, that is 1.5 kilo ohm. That is from a dark condition. So they are saying before the exposed light of, okay. So this is another, I will say, the limit. So given in question, I will say. So this is given in question. Assume that the op amp is initially null. So now if we see, so this is V input voltage. Let's say this is the current I. It will definitely not flow through this. It will flow through this. And will this flow through this capacitor? Now since we are talking about the DC current, so that means there will be no current flowing through this capacitor, because why? If we talk about the reactance of this capacitor, 1 by omega c, so it will leads to, when omega is 0, then it will leads to, xc leads to what? Infinite. So this will be open. This branch will be open circuit. But then you can ask, like, why this was even needed in that case. So maybe this is for the some stability purpose, that so there are a lot of like instability issues when we talk about op amps. So that's why we need a feedback capacitor in that negative loop. So that's why we need that capacitor. But anyway, but in this question we don't require that, so that's why we can remove the effect of that. We can neglect the effect of that. So xc tends to infinity. So what we have, we only have the current I here flowing straight away to 5.5 kilo ohms, and then to the output. Now I think the question is quite easy. So if we talk, so this is 0, so this will be 0. So V in divided by R photocell resistance, RPC, I will say, equals to what? The current I. If we multiply that, this is I. So what will be V naught? V naught will be I into 5.5k. So when I will be minimum in this particular question, so I will be minimum when RPC is maximum. This one. So it will be V in RPC max, that is equals to 3.2. RPC max is 100 kilo ohms, 100k. And why, when I will be maximum, so it will be I max equals to V in divided by RPC. This is minimum, okay. 3.2 minimum in the sense whatever given in the question, 1.5 kilo. So 3.3, sorry, 3.2. So we have I minimum expression, we have I max expression. So when V naught will be max, when I is max. So it will be this, and this will be 3.2 divided by 1.5k into 5.5k. So this will be equal to, let me check, uh, V, yeah. So V naught max will be, like if we just talk about the mod, but minus 10.73, because this is minus volts. And similarly, what will be V naught minimum? It will be minus I minimum into 5.5k equals to minus 3.2 by 100k into 5.5k, which will be equal to minus 0.176 volts. So we have this D as the option. Okay, so this is the range from where this output voltage will vary. Now moving to the next question. Yeah, just read it out. Question, take your time. So we see the question. Then it is saying that what will be the output voltage waveform for the circuit where this we have our 1 CF equals to 1 second, input is a step voltage. Assume that op amp is initially null. So since we see the options only, then we just want to say like will the output will be in what shape the output will be. That's all what we have to calculate, what we have to actually find. So if you just remember your these Smith-Tiggers function generator concepts or like those sessions, then you can like say which type of circuit is this when you have a capacitor at the feedback. So this is kind of an integrator circuit. So if you are giving a pulse like this, then definitely if you integrate this, then you will get a ramp. Okay, so that means for answer for this question will be ramp. Fine. Now the next question. So think of it. Think of it. This, and we have two questions. Yeah, one last. This one question. So let's see this question. So it is saying how to detect the negative peaks of the input signals in the peak detector given below. So they are saying how to detect the negative peaks of input signals in the peak detector given below. So first of all, they are saying that this is a peak detector circuit. Second, they are saying how to detect the negative peaks. Then they have given these options like reversing D1 diode, this one, then reversing D1 and D2 diodes, or then reversing D2 diodes, or changing the position of D1 and D2. So we have to see how things will work. But first of all, uh, the question is like, so if this circuit is not, so what basically initially what this circuit is doing, what is this circuit is doing, what this circuit is doing. So let's see first that. Let's first see that like so we have this pulse. We can say pulse. This is a pulse signal. So this is a pulse. Positive, negative things will be there like that. So now let's see in positive cycle what is happening for the pulse. Positive cycle of signal. So in positive cycle of signal, so this will be what positive voltage, and momentarily I have told you like momentarily the op amp behaves as comparator. Okay, so this will happen momentarily. So because we don't know whether this diode is on or not, and if that is not on, so we cannot get the output, and then the feedback will not be there. So just we are starting. That's why we with the comparator, like the op amp is behaving as a comparator. So we know this zero, so this will be zero. So we have non-inverting terminal of the op amp is having higher voltage than the inverting terminal of the op amp. So that means V in, that is plus, is greater than V minus. So we will have plus V saturation at the output at this point. We can say V naught prime. If V naught prime is plus V saturation, then what will it do? It will make D1 go to forward bias and D2 goes to what, reverse biased. So once D1 is forward biased, okay, that means this part is shorted. If this part is shorted, that means we can just yeah. So this negative feedback loop is in picture. Is- This negative feedback loop came into picture because of the D1 going into forward bias. That implies negative feedback of op amp is there. Okay, so that is there. So that means if so we talk about, okay, for negative feedback, so this becomes short, and whatever the, so V in will be here because of virtual short, and since no current will flow through this because this is connected directly to this, so V in will be here, V naught will be V in, and we will get this capacitor to be charged till V in, that is positive voltage of V input side. Okay, so the capacitor charges to the peak value of V in, positive peak I will say. Now, so now the capacitor has been charged to the positive till the positive maximum voltage of the input. Now the negative cycle will come. Then we'll see. Then we shall see what is happening. Negative cycle of signal. In that case, again that op amp will be behaving momentarily as this comparator. So then V in plus will be then less than V minus, because now this V in is negative, so the non-inverting side of the op amp will be negative, and this side will be higher, that is at, if it, even if it is at ground tension, then it is higher. So that means we will get at output, we will get V naught prime equals to minus V saturation. So if this is minus V saturation, that means D1 is what? D1 is reverse bias. What is D2? D2 is forward bias. So so this becomes open. We are not able to get any output. So this feedback will not come into play. This uh, this circuit will give this will get short from here, and this will be grounded. So this capacitor will remain at plus V in, and it will discharge from 10 kilo ohm. But since this time constant is quite large enough, so it will not get easily discharged. Okay, the capacitor voltage. So in conclusion, so this particular circuit is acting as a positive peak detector, because when positive cycle was there, the capacitor got charged and it got V in as its voltage. But in negative cycle, the D1 become reverse bias, so there is no feedback at the op amp, and the capacitor maintains that V in voltage, although somewhat discharging with that 10 kilo ohm resistor here, but it is maintaining that voltage kind of. Again, when positive cycle will happen, so it will be like again it will be having it will charge this capacitor. So basically this is a positive cycle, is a positive peak detector. But what the question was asking, how to detect the negative peaks of input signal. So now there are different things which this question is saying. So let's see them one by one. Let's see. It's done. Okay. So if we see them, so first option is saying that reversing D1 diode. Now I will clear these things for the clarity. Just hmm. So they are saying that reversing D1 diode. So if we reverse in this way D1 diode, then what will happen? But D2 remains there. So let's go. Let's see. So if we have V in positive cycle, V in is positive. So this is positive. This is again momentarily acting as a comparator. So this will be 0 volts. So we'll get plus V saturation. In plus V saturation, this will be what? Reverse biased, and this will be reverse biased. So it will not be working in positive cycle. But in negative cycle, what will happen? Minus V saturation is there. This will become forward bias, and this will also become forward bias D2. That means this will be shorted. So we will not have any V0 voltage, output voltage. So that means only reversing D1 diode will not work. Let's see what if we reverse both D1 and D2 diodes. Again, I will clear these things just for the clarity. So this is reversed, and this is also reversed like this. So if plus V saturation comes, this is off, this one off, this is also off, nothing happens. But in case of minus V saturation, this will be what? On, because this is in now forward bias, and this will be reverse biased because this is like this. If this is in reverse bias, so this will be shorted and we'll get our V naught voltage. So this will work for for this case, for making this as a peak detector. Okay, so this was about this question. Now the next question. Take some time to read the question. This is also diode based question, and I think so we have to find the output voltage. So if you know the state of these diodes when these operations are happening, then you can comment on the output voltage. But the logic lies whether how well you are able to find the states of these diodes. So yeah, I'll give you some time. So let's see this question. The question says we have to find the output voltage, but for that we need this both diode states. So let's see. So we have 12 volts here. So and initially let's say this was 0 volts. So this is in forward bias. That is fine. D1 is in forward bias. So we will have a circuit. We have this here forward bias, since these are we are considering them to be ideal, these diodes. Then we have this plus minus 10 kilo ohm. Now the question is, what is the state of this diode D3? We don't know. Let's see. This was V0 and a 10 kilo ohm resistor. Now if this is forward bias, then we will have some voltage here, that is 12 into 10 by 12 plus 10, voltage divider rule. Basically some voltage is there that is greater than 0, that is for sure. And this is 0, we have 0 here. So momentarily this op amp again will act as a comparator, because we don't know the state of D3. This is 0, so we will get a positive V saturation here. So if we get a positive V saturation here, that means this is positive and this is 0, so this will also become what? Forward bias. So if D1 is forward bias, then our D3 is also forward bias. So that made this negative feedback loop to come into picture, and we can solve this question. Then this question is little quite straightforward. So 12k, 10k. So this will be what? 12 into 10 by 10 plus 12 equals to 120, 22, 5.55 volts. So again virtual short, so this will be also 5.55 volts. So we will have 5.55 divided by 12k plus 5.55 minus V naught. I'm using nodal here. No current will be in this direction. Okay. So there is some lag, I think. But anyway, so this nodal I am using. So this is 10k equals to 0. So if we solve this, we will get V naught as V naught is approx 10 volts. So this will be our answer. So I think we are done with the extra questions. So today what we learned about these Lissajous patterns, their formulas. Like we did some questions on emitter follower circuits. Now to solve them based on the PMC meter, including that, and then linear ohm meter questions. One question was there, and then some oscilloscope questions. Then we solved some of these operation amplifier questions, and then we also saw that there was some mistake in this I'll say the Researches patterns, which I told you in the last session, and now you can see the corrected version of that. And yeah, so I think that's for all. That's all for today, and I think, yeah, so we will have a next session. We'll take next session on next week Tuesday, and that will be on same time. That is from, I think, 6 to 8. That will be our last session for this course. So see you there, and I will be uploading this YouTube lecture in that YouTube channel, so you can see it from there. And if you have any doubts, any queries, anything to share, like you can share on the discussion forum. And yes, so thank you.